Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is video 19, Route Redistribution Part 2. We're carrying over from the previous video. We're going to use the same network that we had, the same physical and logical setup, but this time we're going to introduce EIGRP in there. So you can see how we set a seed metric in EIGRP, what the seed metric has to be. We're going to look at two different methods of setting that seed metric, and also we're going to do the same thing we did in the previous video, is go around the EIGRP domain and see if we see any suboptimal routing. And that's the kind of thing we have to be able to analyze after redistribution, and we have to be able to say here's why it did or did not happen. That's what really helps us out on test day. We're not just here to memorize commands, we're here to analyze what's going on. And any network diagram that Cisco shows you, you'll be able to analyze it and tell them whatever they need to know. We're going to talk about redistributing static routes for just a minute there after we review show IP protocols again. And redistributing static routes, there's really nothing to it, but the next part where we talk about controlling the redistribution process with static routes, that is huge. Because as Cisco recommends, and as I recommend, and a lot of people around the world recommend, you really want to avoid two-way route redistribution whenever possible. Because what we're doing here is pretty simplistic as far as the number of routes. But when you've got 200 routes coming in, and it would be 200 routes each way if you configured two-way route redistribution, maybe redistributing a static route or a default route would actually be the best case. After we take a look at that, we're going to look at two very commonly confused commands and confusing commands, IP default network and IP default gateway. After that, we'll look at passive interfaces briefly, revisit null interfaces, and how they relate to BGP redistribution. And finally, we'll take a look at distribute lists. Right off the bat, we're going to look at three factors that you must keep in mind when you are performing redistribution into EIGRP. First, we have to have a seed metric. Now we can set that seed metric with either the redistribute command or the default metric command. We're going to look at both. Routes redistributed into EIGRP are marked as DEX and have an administrative distance of 170. In the last video, administrative distance came back on us a little bit after we performed route redistribution, and we ended up with a little bit of suboptimal routing. Let's step back in just a moment and review what we saw in that redistribution scenario from the last video. We had RIP and OSPF. We decided router 3 was going to be the ASBR, but we also learned that you really have to keep an eye on all boundary routers. And here, router 2 is a boundary router. It's not an ASBR because it's not performing the redistribution. But anytime you've got a router in that situation where 2 is, where it's going to get two routes or two different next hops for the same network, we've really got to watch that after redistribution and make sure that we do not end up with suboptimal routing. Now, before we configured redistribution, if router 2 had packets to send to 10110, it had a RIP route and went straight to R1, and then R1 took care of the rest. But after redistribution, we saw that was no longer the case. If router 2 was going to send packets to that remote network, it sent them to R3, then to R1 through the frame cloud, and then to the Ethernet destination. Now, that's not the end of the world, but it's still suboptimal routing. We don't want that. We want the most effective path. And the reason that happened was because the two updates that router 2 was getting for the same network first had the same prefix length. They both carry 24-bit masks. So when that happens, when the network number is the same and the prefix length is the same, administrative distance then comes into play. And OSPF's AD is 110, and for RIP it's 120, and the lowest administrative distance is considered the most believable. So router 2 then started using the path through R3 to get to the Ethernet segment. What we ended up doing was changing the OSPF default AD on router 2 to 200 with the distance command. And at that point, the RIP route then became the primary route to get to the network 10110. But when we took serial 0 down and the RIP route was no longer available, then the OSPF route was immediately put into the table. We had our redundancy, but we were also using the shortest path as the primary path. Now, OSPF has a default seed metric of 20, so we didn't have to worry about that too much when we were in our previous video, but now EIGRP has one, and the official name for it is infinity. I consider that not having a default seed metric, because if the default is infinity, that means we're not going to be able to reach any networks. This is what I have pre-configured for this video, and the only real change is that routers 2, 3, 4, and 5 are now using EIGRP instead of OSPF. Everything else is the same. Routers 1, 2, and 3 are still in the RIP domain. Network 10110 is still attached to router 1 and is being advertised into RIP. So we are going to perform redistribution so that routers 4 and 5 can also reach network 10110. We're going to use router 3 as the router to perform redistribution on in this video. But let's take a quick look. You know, we always do first. Let's run a show IP route and see what the next hop for our border routers are. And let's run show IP route RIP. So we just see the one route. And you see it's got a next hop of 123.1, which is router 1 serial interface, just as we expect. Over on 2, same scenario. Now this is what changed last time. We saw that next hop change after redistribution. Will it change this time? Let's find out. First, we have to configure redistribution into EIGRP. And we're going to go ahead then, just as a reminder, and it's always a little different, but we are going to go ahead and redistribute the connected subnets into RIP. And we don't do redistribute connected subnets, right? You caught me on that. Now, the caret didn't catch me on that because I misspelled redistribute. But we do not set the subnets command there. What we've got to do here is set a seed metric, and we'll just call it a metric of 1. So we're all set there. Now in EIGRP 100, we're going to do the same thing. We're going to redistribute connected networks. But the seed metric is a lot different. We're going to actually have to set 5 of them, 5 separate values, and they are 1 each for each of the 5 metric weights and that EIGRP uses. First, we've got to set a bandwidth metric. We're going to set that at 1544 kbps. We're going to use iOS help to illustrate. The next one is delay. We're just going to pick 10 for that. The next one is reliability, and sometimes people get load and reliability backwards with this, so use iOS help. It doesn't hurt. And we'll set 1500 for the MTU. That's a common redistribution metric for EIGRP. You can kind of develop your own if you want to. That's not something they're going to ask you on the exam. It's something you kind of have to do on your own. Now we're going to redistribute the RIP routes, and we will use the same seed metric. But actually, let's look at the other way we could do this. Now, when we set the metric route, the seed metric here, we are saying that all RIP routes should have a default metric of this, a seed metric. But in the future, we may bring in OSPF routes, we may bring in static routes, we may be planning to do a lot of redistribution here. So instead of using this way of doing it by putting the seed metrics on the end of the redistribute command, what we can do is set a default metric for the entire protocol so that in the future, all the routes that we bring in via redistribution will use these metrics so we don't have to keep typing all these metrics out. And the command to do that is default metric. So we're going to set that instead so you can see both of these in action. And you'll see that iOS help is going to ask us for a bandwidth setting. It's going to be the same order: delay, reliability, load, and MTU. So those are the two different ways with which to perform route redistribution with EIGRP as far as the seed metrics are concerned. We can use the redistribute command, which will set a metric only for the routes that we are redistributing with that statement. Or we can use the default metric command, which changes the entire protocol's seed metric. So now we should just do redistribute RIP, and let's see if that's going to work or not. We set the default metric, and we put the RIP routes into EIGRP. Let's go down to router 4 and see if that worked. And it did, because otherwise we would not be seeing those routes. If you leave the seed metric off and you haven't set a default, you won't see the routes. So far so good. Router 4 sees both the frame network, which is a connected network on router 3, and the remote Ethernet segment on router 1. A couple of things to note here just to reinforce what we've already talked about. You see the DEX next to those two routes. That means that these are external EIGRP routes. They were learned by redistribution. And the AD, as you see inside the brackets, the first number is the AD, and it's 170. And you have to keep these in mind. The reason I'm being a little repetitive with them is because in the CCNA curriculum, most classes and books just mention, oh, EIGRP's got an AD of 90. Well, that's not quite right, but it's not the only AD that EIGRP routes can have. You just haven't seen external routes yet, and you haven't seen summary routes in the CCNA. So just want to keep those straight on exam day. 170 is for external EIGRP, 90 is for internal EIGRP, and 5 is for summary routes. So let's go over to router 5, and we should expect to see the same thing. And we do. Exact same routes, exact same codes, the whole bit. Now, let me ask you this. Before we look at router 2, you remember the scenario we went through last time where router 2 suddenly had suboptimal routing. Will router 2 have suboptimal routing this time? Will there be a change? Right now, what is router 2's next hop IP address to reach network 10110? Is it router 1's serial 0 interface or router 3's Ethernet interface? I bet you know, but you still got a 50-50 chance of being right. I like those odds. Let's take a look. Let's go to router 2. We don't see any EIGRP routes. That's interesting. How about RIP routes? Yeah, that route didn't change this time. That's the route we're concerned about, because we don't expect to see 172.12.123.0 in RIP or EIGRP, because that's a directly connected route for router 2. But this time, the next hop IP address didn't change for router 2. Why not? Why didn't it? Because of the different administrative distances. Router 2 right now is still getting 2 updates to reach that remote network. And one of them, the one from the RIP router, router 1, has an AD of 120. But the route coming from router 3, the one on the Ethernet segment, it's got an AD of 170. So right now, the RIP route is preferred, and that's why it's going in the routing table. Now, that second path is still there for redundancy. If we turn the serial link down, let's tear that link down. We have to take advantage of this because we can't do this at work. Let's shut that link down and see how the routing table reacts once it comes all the way down, and there it goes. Obviously, it shouldn't have any RIP routes. Does it have the EIGRP routes yet? Yes, it does. And you can see now that it sees the frame relay as an EIGRP route. It can still get to the frame. It's just got to go through router 3 to do it. And then, of course, as an extension of that, it can get to the Ethernet segment. It's got to go through 3. So just that quickly, you see that router 2 is still getting the routes, but it wasn't putting these routes into its routing table because it was getting a better AD from RIP. Pretty cool stuff. We like redundancy, but we hate suboptimal routing. So we got to be careful. We're going to open that back up and let that reestablish itself. And while we do that, let's review what we did in the last video as far as administrative distance goes. What we did there with OSPF was change the entire administrative distance on router 2 for OSPF to 200. We changed it on really on a global basis, on a protocol basis. All OSPF routes on router 2 had an AD of 200. And of course, that doesn't change anything on any other router. That AD does not get advertised. So that's one way of doing it. But what we could also do with EIGRP, and we have to watch this one, this is an excellent exam detail, because the command is a little different. We're going to change the administrative distance on router 2 for EIGRP routes as well. But I want to show you this command because it's a little different and it's a good fertile exam question material. Let's first make absolutely sure that everything's back up there. We would expect now to see that Ethernet segment in RIP, and we do, and we should not have any EIGRP routes at this point, and we don't. So we see now that order's been restored, the link's back up, router 2 is getting 2 updates for that remote network. They're both with the same prefix length, so it's using the one with the lowest administrative distance, and in this case, that's RIP, 120 versus 170. Now, we can change the default administrative distance on an EIGRP router, but you have to be careful how you do it. EIGRP commands seem to always be just a little bit different, and this is no exception. It's going to look the same to begin with. We're going to go under the EIGRP process, and we're going to use the distance command, and look at this. Remember with OSPF, we had something that said administrative distance and then EIGRP distance. We actually need to put in EIGRP with this. So we're going to type out EIGRP right here, and we're going to use iOS help to see what the deal is now. Now it's asking for an administrative distance for the EIGRP internal routes. When we change the distance of ADs in EIGRP, we have to state what the internal and externals are going to be, even if we're not changing one of them. We're not going to change the internal AD right now, but we still have to specify a value for it. Do not be fooled into thinking that you can just type distance 200 here and it's going to work. It will not work with EIGRP. We are interested in the EIGRP distance. And now what's the next value with iOS help? The external route AD. So we're going to type in, we're just going to be cute here. RIP's AD is 120, so we'll give these AD of 119. Let's see if that's already taken effect. Not yet. Let's clear our routing table. And you'll notice that tore our adjacencies down on Ethernet, but it came right back up. We don't see the RIP route anymore. But we do see the external route now from EIGRP. And you see why those adjacencies went down? Look back up there. They didn't go down because we cleared the routing table, because we clear the routing table all day long and adjacencies don't go down. It's a little hard to highlight here when one letter starts up here, but I will do my best. Route configuration changed. What that means is the administrative distance was changed on this router. That's going to bring your adjacencies down. Well, it may not be something you want to do during production hours. But the key here is that we successfully changed the administrative distance to 119, and that makes this route just a little more believable than the one it's getting from router 1, and now the next hop is indeed 3113. And we're always going to verify with what? What are we going to verify with? Show IP protocols. And there's EIGRP down here. We could look at RIP for just a minute. And you can always see which version you're running. We're running version 2. Auto summarization is off. You always see where your routing information is coming from. And with EIGRP, we have a couple of different things we haven't seen before. We now have a default redistribution metric. We did that with default metric. We're redistributing, and it's always going to show you connected here and your local protocol, but we're also redistributing RIP into the network, into the AS. Finally, it did show us that auto summarization was off. So it's just that simple. But that's how you have to really be careful with that distance command with EIGRP. And again, working with ADs, working with route redistribution, I highly recommend you either get a couple of used routers. We're going to have a home lab video as a bonus video on this course. You'll see that at the end of the course. And it'll give you some tips on building a home lab. But for those of you with an eye on the CCIE, especially down the road, or you just want to get good at this, if you're like me and you just want to get good at it, what you really need to do is practice it on live equipment. There's no software program that's going to totally give you the route redistribution experience the way that real equipment does. Just saying that out of experience. So let's talk about redistributing static routes for just a moment. The basic redistribution of a static route is simply configured with the redistribute static command. If we just revisit our last configuration here, we'll go into EIGRP 100 and look at iOS help for redistribute. And like I said, most of these are dynamic protocols, and you see some new friends that you've made during this course, on-demand stub routes, that kind of thing, and IS to IS. We've got IS to IS right there. But here we're just looking at static. And you can just type in redistribute static. Since we set a default metric for redistribution, any static routes we have will be put into EIGRP. Now, you can find writing a static route to be really helpful after redistribution. You shouldn't forget about them in other situations, because a static route can actually be used in place of a routing protocol if the router is a true stub router that would only need one route. And we looked here at how to redistribute a static route, but there's another kind of unique static route that you need to know about, and it's a permanent one. And I'm going to give you the theory, and then I'm going to give you some real world advice on this one. To create a static route that will not be removed from the routing table, even if the interface is shut down, you need to use the permanent option at the end of the IP route statement. And there's another thing we can do with IP route. You thought you knew everything about the IP route statement, right? You thought we weren't coming back to that again. The administrative distance of a static route can be changed by specifying the desired AD at the end of the IP route statement. If you've ever used a floating static route, which is a static route we mentioned earlier in the course that will only be used if the routing protocol basically disappears, well, let's take a look at how we would configure that. Or just use iOS help. We're going to just write a kind of a dummy route right here. It's not actually going to go anywhere, but we want to look at the options here. Going to use iOS help at the end, and like I said, you're always finding something new with iOS help. And we see a couple of things here that are suddenly of interest to us. First, the number 1 through 255 in the arrowheads there say distance metric for this route. So we can change the AD of a static route simply by typing in a new distance. What we can also do is type permanent here, and you see it says permanent route. So we could use either one of those options. If we wanted to set the distance metric of this to 213, we would type in 213 there at the end. And let's do show IP route and see if it's in there. Yep, There it is. And the next hop is 123.2. And you see the administrative distance is 213. So occasionally, like I said, for floating static routes, that can really come in handy. Now that permanent option is really a good exam question. You know, how could you do this? In the real world, that doesn't always work terribly well. I don't see that many of them in production networks myself. You may use them where you are, and that's fantastic. I am not saying anything against them. I'm just saying that it doesn't always work the way the theory says it does. You know? And every once in a while we just find something like that that doesn't. It just takes some working with it, much like the IP default gateway command that we're going to talk about soon. But it's good theory to know. We can also use default routes as well when it comes to controlling redistribution, because properly using default routes helps to avoid two-way route redistribution. And again, you don't get in too much trouble with one-way redistribution most of the time, but with two-way route redistribution, boy, you've really got to be careful about every single connection point between the two domains that are downstream. It takes a lot of planning. So let's take a look at this diagram, say. If we wanted each router in this network to be able to reach every other network in the domain, and let's say that each router had, you know, its own Ethernet segment with its own network, we can actually send a default route into one routing domain while one-way redistribution was performed with the other. For instance, in this case, a default route could be generated by the ASBR, which is router 1, for router 3 and 4 to use to go to the other domain, to go to the RIP side, any destinations over there. And meanwhile, you could take the OSPF routes and redistribute them into RIP. This is a fairly common setup when it comes to route redistribution. You're probably going to work with redistributing RIP version 2 and OSPF more than any other protocol combination, because RIP v2 is a very popular LAN protocol. It is used on some wide area networks, and of course OSPF is a very popular wide area network protocol. So if you're going to ever redistribute protocols, these two are probably the two you'll work with. And it's a great idea in this scenario. I've used this in the real world too. It works very well. To avoid two-way redistribution, we would take the OSPF routes and redistribute them into RIP, and then use the default information originate command on router 1 to generate a default route into OSPF for routers 3 and 4 to use to reach any destinations in the RIP domain. Because I'm only showing, I've got one Ethernet segment there on 4, but let's say that we had 75 routes on each side. That's a big load, first off, for router 1 to handle. That's a lot of route redistribution, I should say. So we've got a little bit of a cost there, but what we could really be concerned about is if way downstream in both of these domains there was another router where they could actually talk to each other. Then you have the possibility of a routing loop. So using that default route in OSPF really helps out. Keep in mind that if that router, if R1 already had a default route, then it could propagate it through OSPF with the default information originate command. But if it doesn't have one, then you've got to use default information originate always. Let's take a look at that. Let's bring the rack up. We're not running OSPF on here right now, but that's one of the great things about your own practice lab. You can pretty much do whatever you want. Let's just see if we can see the options here without actually configuring OSPF. Yep, sure can. You'll notice anytime you see the CR at the end here, that means that what you have entered up to this point where you typed that question mark is a valid command. So that means we could hit enter right now and it would work the way it should. but the way it should work is to propagate that default route only if it already has one. What we're interested in here is the always keyword, because when it says always advertise default route, it means it, because it's going to advertise the default route even if the router doesn't have one. And we saw in the earlier redistribution video that what this did is it basically tells all the other OSPF routers, hey, I'm your default gateway. And we saw that change in the routing tables. Now, another command to use for generating default routes is IP default network. And here we're going to compare IP default network and IP default gateway. I'm going to give you some basic facts about it. It'll be enough for the exam. I generally don't teach just toward the exam. I want you to know more about it than is on the screen. But honestly, even if I just read an article to you that I've written about this, it would take an hour. I can tell you where to find it. And Cisco actually has a very solid piece of documentation out there on these two commands. But again, it's a very long example. So we're going to take a look at the basic facts here. First off, with IP default network, if the router has an interface directly connected to the network specified with this command, then that router will generate a default route and send that route to its neighbor routers. May sound a little confusing at first. Hang in there. It gets better. RIP does not have to know about the network configured as the default network, but EIGRP and EIGRP do. And I apologize for correcting that while I was talking. Let's look at that again. RIP does not have to know about the network you configure as the default network. And that may sound a little screwy, which is why the documentation of this gets very long and involved. But EIGRP and EIGRP do. There are two ways we can do that: by using the network statement or by redistributing a static route. That's good stuff to know. One other thing to keep in mind about EIGRP, and you may never actually configure EIGRP in your life, this is probably the only piece of information you need to know about EIGRP for this particular exam. EIGRP does not recognize a route to 0000. So you cannot redistribute a static default route into EIGRP. So for EIGRP, if you're trying to use IP default network, I would use the network statement. Now again, the documentation on this, it's solid, it's worth reading. It's beyond the scope of the exam, but I want you to be better prepared for the exam. I want you to be prepared to work with the stuff in the real world too. And you do see these commands out there in production networks, particularly IP default network. So again, a couple things I would do a search in that on Google or whatever your favorite search engine is for IP default network. The first match will probably be an official Cisco document referring to IP default network, IP default gateway. And also, I've written an article that's gotten a lot of distribution out there on the net. So if you put these two terms in there, you'll probably see it on the first page. You want to put my name in there, that'll probably help. And you can certainly read that on your own time. I think it's well worth reading because these two commands do get confused. And IP default network, my experience is it doesn't always work as well as it should. But again, it can be because it's just a very tricky command to get started sometimes in a large network. Here's the key. We're going to boil this down. I've got some facts on here that you need to know for the exam. It's good stuff to know. But here's the key. You use IP default network when IP routing is on. The only time that you'll ever use IP default gateway is when IP routing is off. That's it. Like I said, getting IP default network working doesn't always work the way it says in the books and the documentation, but to keep them straight in your head, I would simply say to you that the only time you will use IP default gateway in your life is when IP routing is off on the device that you're trying to use it on. Okay? Passive interfaces, CCNA stuff here. You know this already, but I'm going to mention to you the definition anyway, but I'm also going to tell you something that you'll hear some people say passive interface doesn't do, and we're going to disprove that. Passive interfaces accept routing updates, but don't transmit them. If you've taken my earlier courses for the CCNA, or you've worked in any of my labs, you remember that we put passive interfaces on the BRI interfaces if we did not want them to transmit update packets. But you can do that with any interface. Keep in mind that what you do, however, with that command, we'll bring this back up and go back under EIGRP. We'll do it on RIP, on router 1. We're going back to this network that we had up previously. Give me just a second here. We're going to go back to this network, and we're going to make S0 passive there for router 1. And of course, you know what's going to happen when we do that. Router RIP, passive interface. Of course, then we name the interface. And to take it off, we simply repeat the command and put no in front of it. When I type passive interface serial 0 there, serial 0 will still accept routing updates, but will not transmit them. I know you know the definition, but the reason I bring that up is to remind you of something that really does trick a lot of people, and that's simply that the command is called passive interface, but it does not go on an interface. It's configured under the routing protocol. Good detail to keep in mind. Now, you've heard that you can't use passive interface under OSPF. You may have heard that, I should say. And the reason kind of makes sense that people say, oh, well, you can't make an OSPF interface passive because they're not really transmitting updates. And yeah, that's true. They're not transmitting routing updates the way that we understand them from our RIP, IGRP, EIGRP studies. They're transmitting LSUs, which contain LSAs, and then you know the drill from there. But notice that this router doesn't seem to have any problems with me naming an interface as passive under OSPF. Now, I'm not running OSPF on R1 yet, but just to illustrate that I can do that. You can make an OSPF-enabled interface passive. And what happens is, when you do that, is that you are preventing any OSPF traffic from exiting that interface. OSPF traffic, you know what that includes? That includes hello packets. So if you do that, you're not really you're going to prevent routing updates in a way, because no OSPF adjacency can be established through a passive interface. Can't do it. You will see very rare instances in your career where this comes in handy, but I have used it. I stopped hellos from going at an interface where they were not really needed, and I basically had somebody scream, well, you can't make an OSPF interface passive. Well, as the great philosopher said, oh really? I'm pretty sure I just did. That's exactly what I did. So we can use passive interfaces with OSPF. It's just not something you're going to do a lot of. Now we're going to talk about that null interface and the null 0 interface and BGP redistribution. So hang in there with me on this, because it may seem a little off at first. You'll think, well, why would we do that? We can configure a static route with null 0 as the exit interface. You probably never noticed that. If you use iOS help to fly around a lot, you may have noticed it. If you did, good for you, because I didn't notice it for a long time. Let's see, 172.12, 123.2. Let's use iOS help here at the end. Oh, went too far, because that's where we put the interface. So at this point in an IP route command, we can put the next hop IP address, you know the drill here from earlier videos, and we can specify the exit interface. But notice in the middle of all this, null interface. Why would we ever configure a static route that goes nowhere? Because if a packet matches an IP route to null 0 or any route to null 0, what happens? The packets are dumped. So what we do this for is actually to allow BGP IGP route redistribution. And again, BGP route redistribution is a very complex subject, and you'll master that during your IE studies. But we need to touch on it now and give you a little background for the exam. We want to avoid redistributing specific routes from an IGP into BGP because there's always the chance for error that we're going to let routes through that we didn't really mean to. What we can do is create a null route and redistribute that static route into BGP. And basically what you're doing there is you're aggregating the routes before you put them into BGP. Let's take a look at an example of that. We have 3 IGP routes. Let me just move that in line there. Thank you. We have 3 IGP routes, 150, 101, 2, and 30, all with 24-bit masks. And we want to redistribute those into BGP. So what we could do, instead of just performing IGP, BGP redistribution and getting all tense and saying, boy, I hope I don't mess this up, I would summarize those routes and then put the summary into BGP. Now the summary that I'm sure you were able to come up with is 150.100.00/22. And the IP route then that we would write is 150.100.00, first 22 bits of the mask set to 1, and then come up with the null 0 interface and then put that into BGP. Now this will not impact your IGP routing at all because the 3 routes that you already had in it have a longer prefix than this. So any packets that are destined for any of these 3 networks are going to follow whatever next hop is next to these more specific routes. They're never going to be sent to null 0. There's one more use for doing that, and that is to trick BGP into thinking the IGP has a route for a destination that it really doesn't have. If you ever face a situation where you need to redistribute a route into BGP from your interior gateway protocol, and that network didn't exist in your IGP table, you could create a route to null 0 with the IP route command and then put that into BGP. Then BGP is going to say, oh, okay, the interior gateway protocol has a route and everything's great, but it really doesn't because the route is to null 0. You're kind of tricking BGP. Again, a very specialized situation there, but a good one for you to know. Moving on to potential issues regarding BGP redistribution. And this is quite a potential issue here. If we screw up redistribution with our own IGPs, we're going to inconvenience some people in our company, but we're not inconveniencing the world. Well, a full BGP table can actually hold over 100,000 routes. And you should carefully consider that fact before you start working with BGP redistribution, because a lot of damage can be done very quickly to your network. First off, if you redistribute BGP into your IGP and you bring in 100,000 routes, your local router is probably just going to have a heart attack right there. And you can also actually damage worldwide internet connectivity if you're taking some BGP routes out or putting some routes into it that shouldn't be there. So again, it's something you do only at an expert skill level. And again, the only place to get practice in doing this isn't in a home lab, and that's not enough practice. It really isn't. You'd have to do it or be trained by someone who's got a lot of experience in performing BGP redistribution. But there is another problem you need to know about. If the IGP routes were dynamically learned in the first place, then they may have been learned from BGP to begin with. And then putting them back can very quickly lead to a routing loop. In the drawing here, R1 is redistributing a BGP learned route into OSPF. And that's going to be fine until it gets down to the other edge, the other boundary router for OSPF, R4, and R4 is redistributing the route back into BGP. And you can just take a quick look at this and say we have one big fat mess here. We have a routing loop. Because again, whether BGP is involved or not, and again, I don't want to dissuade you from learning redistribution. It's a great skill to learn, but you've got to do it and get a lot of practice in it in a home lab or on a rack rental. Because when you're configuring route redistribution in a network with multiple paths like we've got here, you got to be really careful. This is where default routes and static routes can be very helpful. And if you just can't avoid two-way route redistribution, use your skills to change the AD, change the default metrics, some kind of route filtering, but just make sure that you plan correctly, and then you'll be on your way to a successful redistribution scheme. Now, with all our concern about route redistribution, we need another tool to help us out as far as filtering routes. Because even beyond the more complex scenarios that we've looked at, like the one on the board right now, where we may not want all the routes coming over into an OSPF domain that we're redistributing from RIP. Maybe we just want a few. And what will help us in that is configuring a distribute list. And a distribute list command is going to call an access control list. And the ACL itself is going to permit or deny routes. And if they're permitted, they can be redistributed. If they're denied, they're not going to be. You really need to keep an eye on that implicit deny, obviously, in this situation. You can use a standard or extended ACL for this. I've always used a standard unless we were just out of numbers and had to use an extended, but you can use either one. Officially, they serve as a basic form of network security. Again, I wouldn't throw my PIXs out if I were you or my other firewalls. But what you can do in this situation, let's say you had 10 routes that you were bringing in from an OSPF domain and putting them into an EIGRP autonomous system. Maybe there are 2 networks over in the OSPF network that you don't want anybody downstream in the EIGRP AS to even know about. So you could quickly configure a distribute list to allow distribution of the 8 routes and deny redistribution of the 2 networks that no one else is supposed to know about. So it's a little bit of a security feature as well. I will point this out on the router also, but note that distribute lists can be enabled for the entire protocol or per interface, but either way they're actually applied at the routing protocol level, and you'll see that in just a moment. With an example that I've pre-configured on the routers, routers 1, 2, and 3 are communicating over the frame relay network, and they're all running in network 172.12.123.0, and router 1 is actually running RIP. Actually, they're all running RIP, but router 1 is the only device that is actually advertising a couple of networks. And right up here at the top you see 3 loopbacks, loopback 0, 100, and 200, with corresponding, let's turn the debug off here, corresponding IP addresses. Let's go back down to the config. We're going to look at the RIP config right here. You can see it's running version 2. It is running over the network 172.12.0.0. Auto summarization has been disabled. And I have already configured route redistribution. I'm redistributing those 3 loopbacks into RIP with a seed metric of 1 because RIP does require a seed metric. Let's go downstream to routers 2 and 3, and we see that router 2 sees all 3 of those networks. Let's go over to router 3 and make sure we're okay there. And we are, so everything looks good. Well, maybe we don't want all of our connected routes to be redistributed downstream. Maybe the only one of these 3 that we want is the 100.110 network. So we're going to go back up to router 1, the point of redistribution. And the first thing we're going to do is write an access list that names that particular network. Always use a wildcard mask. And we do not have to write deny statements here because the implicit deny is going to deny any other routes. So the only route this ACL permits is 100.110/24. And now we're going to go under the RIP process and apply it. And I'll show you what I mean by the two different levels we can apply this at. Distribute list is the command, then the ACL. And I'm going to use iOS help here because we are filtering them either in or out. And as you progress in your studies, you'll see that applying this with OSPF can be a little tricky because OSPF does not really send routing updates. So for those of you with home labs, or if you get some remote rack access, I'd practice with that a little bit. I don't think you're going to see it. As a matter of fact, you're not going to see it in your BSCI exam. That's more of a CCIE level topic. But just watch those distribute lists with OSPF and IS to IS. So we're going to say outbound updates are going to be filtered, and we use iOS help here, and we see a list of interfaces. We also see a list of protocols, and at the very bottom we see the CR in the arrowheads. And what that indicates, of course, is that this is a valid command as is. That would apply this filter to all updates being redistributed into RIP and then sent out. It would filter them. If you had this going on, if you had RIP routes going out serial 0, serial 1, and Ethernet 0, by just hitting create right here or enter, that would apply it really globally. But we're not going to do that. We're going to tie it down to serial 0. And it's just that simple. Now, being RIP, we're going to go ahead and clear the routing table. Actually, let's run a debug IP RIP and clear that routing table. Let's see what we see here. There are some updates coming in. And you can see there building flash update entries. And the only entry in there is 100.110/24. This is why I talk about running debugs a lot. You can actually see what's going on. Because otherwise we're just typing commands and hoping they work. And you can see building update entries. So I think that's the only route we're going to see as we go downstream. We'll leave that debug running for right now. Let's go down to router 2. And we see all three. Now let's try clearing that routing table and seeing what happens. Now we've got that. Don't forget that, because it's really easy to look at a RIP or EIGRP table downstream and say, oh, I'm not getting the results I want. Always clear the table again, because you can see that these two routes that we're no longer allowing, they were starting to time out. But you and I both know how long that can take with distance vector. We could be here an awfully long time. So you could see that it had been 1 minute and 11 seconds since the router had heard about the two routes that we're filtering. But the way the distance vector converges, which of course is slowly, it wasn't exactly up to date. And it had been only 16 seconds since it heard about 100.110. So we'll run show IP route RIP, and we're fine. We'll do the same on 3, and you see that the 3 routes are still here. And a less experienced engineer might say, oh, what's going on here? But we know what we're looking at here. It's been 2 minutes and 13 seconds since this router heard an update about those two routes, but again, because of the nature of distance vector protocols, the routes are still in there. So we're going to clear the routing table again and do a show IP route RIP again, and now we see that only the one route came in, just as we expected. So distributed lists, I'd get some practice with those. Like I said, the combinations are almost endless, because you can just apply it to the entire protocol. You can apply it toward routing updates going out certain interfaces or being redistributed into certain protocols. It does take some practice to get used to the more advanced scenarios. Good CCIE level stuff too. Really is good stuff to start getting your hands on. One more warning, if you will, about route redistribution. And this has to do with OSPF into BGP. And I know that you're tired of hearing about how dangerous that can be. But there are a couple of options here I'd like you to know about. And actually, we'll bring them up on this screen. And I'll just create a router BGP 100 process. And we're going to look at redistributing OSPF into BGP. And you've seen a couple of these already. We haven't used route maps yet. And again, that's a more advanced scenario. VRF, we're not worried about that right now. We've been using the metric, but this match is interesting because you see next to match it says redistribution of OSPF routes. When you're redistributing routes into OSPF routes into another protocol, it can get a little confusing. And in this scenario, the only thing I really want to point out to you is that if you are redistributing OSPF external routes, you have to go through kind of a long command to do so. Now you recall that with OSPF we have two types of external routes, E1 and E2, the E2s being the default. Keep in mind here that if OSPF is showing external routes, it learned about them through redistribution in the first place. So if you're redistributing those again, you better be really careful. But we need to know how to do this. So if we're looking at an external route redistribution, we have to use this match command. And then we've got some options after this, and you can see external, internal, or NSSA-external. And we're looking at external routes here. This may be the longest command you've typed to date. External. Then it's going to ask me, well, do you want type 1 or type 2 routes? So like I said, redistributing OSPF in another protocol can be a little convoluted. Okay, so I want to redistribute external type 1 and external type 2. Can I just type a 2 there? No, I can't do that. I have to type external again, then 2 here. So that is actually the full command for redistributing both kinds of OSPF external routes into another routing protocol. I use BGP because that's probably the only time you're ever going to do it, and even then probably you need to be really careful in doing it. But if we are redistributing both kinds of external routes from OSPF into another protocol, we've got to use the match command, and then we've got to use external 1, external 2 on the very end.